welcome everyone. Today I'm very happy to speak to Saira Hamid from the Arizona State University. And she and her co-workers, they just recently published a study on Mars, where they look at explosive volcanic eruptions in the older history of Mars, so 3 to 4 billion years ago, and how they might be responsible for ice deposits in the equatorial regions of Mars that we can still observe today. So before jumping into the actual depositing of the ice that you're suggesting and modeling in your study, can you talk us a little bit through the explosive volcanic eruptions that we had on Mars 3 to 4 billion years ago? What are the traces we see today that we can say there were those events? And also, can we imagine those explosive eruptions on Mars similar to how they would look like on Earth?
Yeah, thank you for that introduction. I'm very excited to chat with you today. So Mars is a very interesting planet, volcanically speaking. It has these massive volcanoes all across its surface, Olympus Mons being the tallest mountain in the solar system. And so you find all these volcanoes that occupy terrains of different ages. So Mars is split up into 3 primary geologic periods. So there's the Noachian, there's the Hesperian, and then there is the youngest, which is currently in the Amazonian. And you have these volcanoes on the oldest terrain called the Noachian. In particular, you have these volcanoes such as Apollinaris Mons and Syrtis Major, which are near the equator, and they're the volcanoes I include in my study. And they don't look like your typical Hawaiian volcano, which are characterized by these sort of gentle-ish lava flows. They have evidence that they've been carved out by channels of perhaps fluvial or water channels, and they have other observations that are consistent with a more friable or just a more loosely consolidated material, whereas with shield volcanoes like Hawaii, they're more hardened due to the cooling of lava flows. And they're really, they spread out in such a way that is indicative of ash deposits around the volcano. And earlier in Mars's history, the atmosphere is thought to have been denser, and that could have facilitated explosive volcanic eruptions for a variety of reasons. But also, Mars's low gravity could have facilitated explosive eruptions, making it easier for plumes to reach taller heights. Things going on in the interior make it easier for gases to escape and explode into the atmosphere. And so multiple things kind of coming together could have made it so explosive volcanism was pretty common on early Mars. And so we decided to see what happens if we simulate explosive eruptions of water, which is a common volatile or gas that comes out of volcanic eruptions on Earth. And there's multiple lines of evidence that the same could have been true on Mars. And yeah, we find that they deposit along the equator where you get this excess hydrogen. And this excess hydrogen could be hydrogen bound up, chemically bound up in minerals. It could be water ice, and so it's really interesting because these volcanic eruptions appear to be relatively overlooked in how they could actually deliver ice to the surface.
Cool, thank you. I think this was a very nice textbook review of what controls explosive volcanic eruptions, and it's nice to see it transferred to Mars, in particular with its lower gravity. Yeah. Okay, so I think you already tapped quite into my second question. So what you are proposing in your study is that water is released during those eruptions, and then the water freezes, or at least helps to freeze either ice aggregates or ice ash aggregates, and they then deposit at the equatorial region. So can you walk us a little bit through this process and also give us some insights on the climate model you're using to back up this theory?
Yeah, so in terrestrial volcanoes, so volcanoes on Earth, if the conditions are right, you because there's such a large influx of water that comes from these explosive eruptions, eruptions have been classified as these dirty thunderstorms. And that's because in the volcanic plume during the eruption, you have such a high concentration of water. And that paired with the high influx of volcanic ash allows that water to condense onto these ash particles in the atmosphere. And it's very similar to how cloud formation works and how precipitation works. So if you have enough particles in the atmosphere and water is able to condense on it, over time, more and more water condenses, and then that water eventually falls out of the atmosphere. That's why we get rain, and if it's cold enough, that's why we get snow. And me and my co-authors, we thought it would be an interesting idea to simulate this process on Mars because we already, see evidence of volcanoes all over the surface. So it's not that much of a stretch to say, hey, let's test how it would look if we can simulate explosive volcanic eruptions. And yeah, we find that, so we use the LMD, which stands for the Dynamic Meteorology Laboratory Planetary Climate Model. This is a climate model born out of a team based in France. And so their climate model allows for the simulation of really any planet with an atmosphere. And so we've been in close contact with the team to learn how to use the model and kind of get it working to get it adapted to be able to simulate explosive volcanic eruptions on Mars. And working with that model is a three-dimensional global climate model. So we can simulate the atmosphere of Mars from the surface up into high up in the atmosphere. And it can allow you, it takes into account the topography of the planet, it takes into account different processes like cloud formation, it allows you to simulate the prevailing winds that are occurring on the planet, and it allows you to simulate early Mars as well. So you can increase the atmosphere to an Earth-like atmosphere pressure of 1 bar or 100,000 pascals. And so we essentially just told the model, hey, at this particular coordinate and at this particular height, release all this water into the atmosphere. And we find that because Mars is so cold, even back when it had a denser atmosphere, that this water immediately freezes out as ice. And then you get all these really neat circulation patterns that allow for water to really accumulate all over the surface, but it seems to preferentially deposit in these regions that align with the excess hydrogen from orbital observations of Mars, which was a really, really cool finding. I remember when I first started running some test simulations, I was at first just focusing on, so you can focus on different states that the tracer or the water occupies. So I was just looking at ice that landed on the surface. And then just, playing around with the model, I looked at another parameter that controls precipitation. And then it was super interesting seeing how much the volcanoes in my model could contribute to precipitation all over the planet. And it's really interesting because when you think of precipitation, you don't, at least in my mind, I don't immediately go to volcanoes and how does that, cause all these like localized weather impacts. You usually think of precipitation coming from clouds and, it's an overcast day today and then it rains and then there's a thunderstorm. But, these volcanoes could have brought a lot of localized and even global weather impacts that have been kind of underappreciated, I believe, so far.
Yeah, definitely. I mean, you can also see this on Earth, right? If you have large enough eruptions that they would impact the weather, at least very locally. So then I wanted to ask about the ice deposits in the equatorial regions. Is it 100% clear that these are ice deposits, or I think you already touched this in the beginning, or could it also be something else like hydrogen in any kind of form, or can it be a mixture? And also, how thick are these deposits that have been detected there?
Yeah, so it's not 100% certain whether these are ice deposits. So we know there's excess hydrogen coming from the surface of Mars because of orbital data from various missions that use different gamma ray or neutron spectrometers. And essentially, it can measure how much hydrogen is leaving the surface. And it can kind of translate that hydrogen to, with some assumptions, to the amount of weight percent of water that would be present in the surface. And, there are some parts of the equatorial region that are higher than the rest of the planet that's more drier. But they have still a few weight percentage points of this water equivalent hydrogen. But then around these regions called the Meridiani Planum and also the Medusa Fossae Formation, you have these really high areas of excess hydrogen, and they just about match the amount of excess hydrogen you get at the polar regions, which we we're pretty sure about has water ice there. And so while this particular instrument only measures within the first few centimeters of the surface, so we don't quite know how deep these potential ice deposits could be. But with regards to the Medusa Fossae Formation, there have been radar investigations into that region. And I can't think of the depth of how deep radar can penetrate off the top of my head, but that could be pretty complementary in probing the subsurface because there are lines of evidence that there's ice deposits much deeper than the first few centimeters of the surface from radar observations. So I think looking at the neutron spectrometer data as well as radar investigations allow us to kind of say, this excess hydrogen might be the really high amounts of excess hydrogen might actually be water ice. Mm-hmm. And perhaps it could be a combination of water ice or water that's bound up chemically in minerals. And I talk in the introductory portion of my paper about like all the different possibilities of what this could be. But definitely there is probably some water involved in these signatures.
And how can we explain that this water ice is still present now 3-4 billion years later, and it's not lost into the atmosphere through, I don't know, sublimation, for example?
Yeah. So a lot of the water that was probably present on early Mars has either gotten locked up in minerals on the surface or has been sublimated and lost to space. And there's seemingly a prevalence of water that's been trapped at the poles and also near the equator. And so the polar regions make sense because it's so cold, it's able to kind of trap water there for very long periods. The equator doesn't make as much sense how it could survive for that long, considering Mars's obliquity is actually very close to Earth's. So Earth is 23.5, and then Mars is about 25 degrees axial tilt. And so near the equator, you get a lot of sunlight hitting the ocean. And in theory, any water ice in those regions should sublimate, kind of like how they do on Earth, unless you have these really deep oceans, which Mars unfortunately doesn't have. Yeah. But in the paper, we hypothesized that if you have an ice deposit, co-deposit with ash, or get covered by a layer of dust or ash, that can actually protect this water ice for long periods. And it could potentially protect it for billions of years, depending on how thick that ice layer is, depending on how quickly you can form a cap over that ice deposit. I believe it was the Phoenix lander that landed on Mars back in the 90s. It landed and it scooped up a piece of Mars, and it revealed like a layer of ice just beneath the thin layer of dust and regolith on the ground. And who knows how long that ice has been there? It's this is an area that hasn't been disturbed by anything else besides like impacts or anything like that. And so there's a lot of people who hypothesize that this layer of dust or ash could preserve the water ice for very, very long periods. And we're talking eruptions that have been ongoing for millions, maybe even longer. And so if you have an eruption or if you have a volcano that's constantly spewing out water over time, then that might allow for these deposits to build up and remain pretty resistant to sublimation.
Yeah. Cool. Thank you very much for walking us through your study. So from this point onwards, is there any follow-up work you plan to do on this topic?
So this work has been one part of my broader story that I kind of discussed in my dissertation. So my dissertation is focused on volcanic eruptions and how they influence the atmosphere, the climate, and the surface of Mars. And my first study, which was released last year, focuses on, so I have 3 studies total out of my dissertation that focus on a different volcanic style. The first study from last year was focused on passive degassing. So what is the impact of passive degassing, or this non-eruptive degassing and release of water into the atmosphere, have on the Martian environment? This is something that typically all volcanoes exhibit when you have a magma beneath the surface reach a certain depth. Then the volatiles, or the gases, can exhaust due to the lack of compression that was available deeper in the subsurface. And so you start to have degassing of these volatiles in the atmosphere. And so I looked at that process and how that could influence surface ice accumulation around the globe. And then I'm also very, very, very close to publishing another study that focuses on effusive volcanic eruptions, in particular flood basalt eruptions coming from this one region called the Athabasca Vallis. And this is a region that is thought to be very, very young, could have erupted within the past few million years. And so we're modeling the effect of water release from these flood eruptions. And so flood eruptions are, you can think of effusive eruptions like the Hawaiian style of lava flows, but it happening over a greater spatial extent. So going on for miles or kilometers and kilometers. And so that's another process I model. And then I have this explosive volcanism and paper looking at the effects that explosive volcanism have on the Martian environment. And so this work has been a part of a really fun 3-part story into how volcanoes influence Mars. And kind of looking forward, I'm actually trying to make my way back to Earth. So when I first entered this field in undergrad, I had my start with terrestrial geology. So going around studying volcanoes on Earth and learning from being here on a planet that is also very volcanically active.
Yeah.
And I've always been really, really fascinated with astronomy and with space and everything, and that's what drew me to want to study Mars. And so that's why I went to ASU, and then when I went to ASU, Arizona actually has a lot of volcanoes, fun fact, and I had the opportunity to kind of relate terrestrial volcanoes to what we might expect on Mars. But now I'm thinking of kind of bringing it back home to Earth, kind of getting back to my roots and looking at the interplay between volcanoes and atmosphere, but also looking at kind of focusing more on atmospheric processes as well. And my research now is kind of taking me into the atmospheric microbiome. And so incorporating not just volcanology and atmospheric and climate science into my research, but also microbiology. And so I just graduated last December from Arizona State, and now I'm a postdoc at ASU. And now I'm kind of like learning more about microbiology and seeing ways they might overlap with volcanology, atmospheric science, and everything. And so that's sort of where my future work is, broadly speaking. That's the direction I'm going to be going. And so I don't have any immediate publications with regards to that work at the moment, but I'm using this time to do a lot of learning. That's the kind of great thing about being a postdoc, is that you have a lot of freedom to kind of explore and find yourself as a scientist and everything. And so, yeah, it's been really fun.
Yeah, sounds like it. Thank you very much for talking us not just through your paper, but through all the work you did. It sounds very exciting.
Oh yeah, no, it's really fun. I mean, I really loved working with this global climate model. I tell people it's like almost like a video game. You're making a virtual planet, and it's just really, really fascinating to be able to play around with the different parameters and kind of make predictions about what could have happened on early Mars. And while I am kind of making a transition to sort of focus my efforts on Earth, I'm not totally saying goodbye to Mars. I don't think I ever could. And so I'm really, really interested in delving a little bit more into understanding the climate of Mars and how volcanoes could have influence the climate. And so in my paper, I touch a little bit about how the release of sulfur, particularly sulfuric acid aerosols, could have caused Mars to plunge into a global winter. And this could have helped preserve any surface ice deposits that might have landed on the surface. And it's interesting because you have volcanoes on Earth exhibit this characteristic as well and release sulfur into the atmosphere, and that has reached high up into the atmosphere, into the other layer of our atmosphere called the stratosphere. And that it kind of, when things get up in the stratosphere, they can get stuck there for a little while, because in the troposphere, in the atmosphere that we occupy and we breathe, we have weather, we have precipitation that, you know, can latch on to these sulfur aerosols and draw them out of the atmosphere. But when they're in the stratosphere, they get stuck there for more extended periods, and they can actually reflect sunlight away from the surface. And that has been shown to lead to these global cooling impacts on Earth from a lot of different volcanic eruptions, with the Pinatubo eruption being one significant one. That one occurred in 1991, and global volcanic induced winters has been a topic of discussion for some time now. And that's also a process we included in the model as well. And we found that due to Mars's atmosphere and the lack of these widespread weather events, as in the case of Earth, a lot of that sulfuric acid, since I'm not trying to get into too much detail, because Mars's weather is extremely complicated, especially when talking about Earth's weather. But in short, because we have an ocean, we have a lot of cloud formation, we have a lot of precipitation and everything like that. So we have more, it's more active. Whereas on Mars, it's a little bit drier, and you don't have all those opportunities to remove all of these aerosols from the atmosphere as quickly. And so we find on Mars that, the sulfur can also plunge it into a global winter. And so I thought that was a really interesting thing to kind of figure out during this study as well. And kind of looking forward, I'm really interested to explore a little bit more about how these volcanic eruptions could have influenced the environment. Right now I look at how could they have supplied water to the atmosphere and the surface. But it would also be interesting to see how they would affect existing reservoirs of water on the surface. If Mars was occupied by lakes and rivers and things like that, and deltas, and it would be interesting to see how volcanic eruptions could have influenced a planet that was a lot wetter in its past. Especially because there's been a lot of talk about the recent NASA discovery, and there are implications for how volcanic eruptions could have helped facilitate habitats for microbial life. So I touch on this a little bit at the end of my paper about how, these ice deposits could have housed an environment for microbes. If you were to go into Antarctica, a region that's relatively analogous to Mars in terms of its dryness, but still the prevalence of ice that was likely present on early Mars. And, if you were to go there and dig up in some of the glaciers or things like that, in your scoop, you'll find little microbes in there. If you look deep into glaciers, there are these liquid water pockets in that occupy some of the cavities of glaciers. And in those with the water pockets, you can find microbes that love cold weather, essentially, or love cold
Yeah.
environments, and can, potentially thrive in those conditions. And then you have these nutrients from volcanic ash, such as iron, that could help fuel the metabolism of different microbes. And so these volcanic environments could be environments that NASA might want to look towards in the future to find these signatures of and evidence of life. And so I think it's pretty timely that this NASA discovery is coming out. That team is kind of looking at data that was returned from an ancient lake bed. But you know what? There could have been habitats around volcanic areas that could have allowed microbes to survive. So, NASA, maybe future missions can go to volcanic regions.
You mean people up there? Yeah, then we would know because they, could go to the right places. And
send a rover to a volcano. Send astronauts to a volcano.
Yeah.
You might be surprised by what you find.
Yeah, and that would be so cool as a geologist to walk over Mars and start looking at the rocks, start digging, to actually see what's up there. Yeah.
Oh yeah, like imagine as a volcanologist going to a volcano on Mars. The volcanoes on Earth pale in comparison to the volcanoes on Mars. They are extremely large due to a variety of different reasons. But, just walking up to this massive geologic structure, I mean, that would be truly alien.
Yeah. Yeah, I fully agree.
Yeah.
Well, I don't know. So now there are plans like this, I think, Artemis mission, right, to send people to the moon. Are there already fixed plans with NASA to send people to Mars? Like really fixed?
Nothing fixed yet. So the hope with these Artemis missions is to provide a pathway to be able to get to Mars.
Yeah.
And I think that's a really good idea because human exploration is extraordinarily difficult. And, we still have a lot to sort out. Although we've been to the moon during the Apollo missions back in the 60s and 70s, those were for very, very short periods, like a few days at a time. And then the journey to the moon is only a few days at a time. So we have a lot of learning to do on how to create a long-lived habitat that astronauts can occupy, how to live off the land potentially and not have to carry all of our resources to another planet, which can be extremely expensive and very, very difficult to do, to carry all that mass with rockets. And we have a lot to learn about how space affects our bodies. For decades now, there have been astronauts on the International Space Station, and we're still learning how space affects things like our eyes, our bones, or everything. And that is under the protection of Earth's magnetic field. And so the magnetic field is able to block away some solar particles and, energetic particles that might harmfully affect humans. And so I think we have a lot of learning to do before we're ready to send people to Mars. But all of the human exploration we do is with the hope of, going to Mars. It's called Moon to Mars. That's sort of like the phrase that NASA uses. And I think if we keep on, if we go and learn a lot about, the planet we're on and, the moon and space and kind of what that means for humans, I think we'll be more than ready to get to Mars.
Yeah. And who knows, maybe we'll live long enough to see this happen.
Maybe at least astronauts can like fly by Mars or
Yeah.
something.
Yeah.
We'll see.
Yeah.
We will see. I hope so too.
So yeah, thank you again for talking us through your study today and much beyond, because this was much more extensive now than just your work. But everything, of course, related to your work. So this was really very interesting to chat about. So thank you again very much for your time.
Thank you for having me. I love chatting about these things and all things the natural world. I have a website. I'll make a shameless plug. It's
That's
just
fine.
My first and last name, so saira-hamid.com, and that's where all my socials are and everything. You can find me there, and if you want to keep up with any of my research or anything I'm kind of up to now, you can do that by going to my website. I have all the relevant links there about my socials and my publications and everything. So thank you again. This has been very fun chatting about Mars, Earth, and life and astronauts. And I love having these discussions. So yeah.